Okay, so we're going to be talking about resistors in combination today. So, as you already know, resistors are something in circuit that can resist the flow of charge or the current in a system. And it's just as basic as that. So we're going to start off with thinking about how resistors would act in combination with each other. So let's think about a series of resistors. So a series is when we have two resistors that are in line with each other in a circuit. Now let's call this 1 and 2. As we know from previous discussion about how circuits work, we know that we have something called Ohm's law. And Ohm's law states that the current is going to be equal to the potential difference divided by resistance. So, if we think about this in series, we know that the potential difference across resistors is they're not equal to each other. And we know that current across resistors in series is always equal to each other. And we know this because, okay, let's use a river analogy. If we have a really wide river, and it's flowing through something wide like this, and then all of a sudden it has to go through a tiny little straw. All of the water that is flowing through this large section of the river here has to go through this. There's no way to go around it. There's no way to cut through or anything else. All of the water has to flow through this. So we know that the current here, or water, the current of water here is going to be the same as the current of water through here, because it's going to be the same amount of water molecules right here as it is right here. It all has to flow through that. And we can think of the same thing with resistors in series. We know that current is the flow of positive charges, and we know that all of the current that is going to flow through resistor 1 also has to flow through resistor 2. So we can use this to think about how different values of resistance will be in a series. So, as we know before, the current is going to be equal to, the overall current of the series is going to be equal to the current flowing through resistor 1 and the current flowing through resistance 2. And we also know that the potential difference is going to be different. We know that the potential difference across the series, across the battery, is going to be the potential difference across the first resistor plus the potential difference across the second resistor. And then what we can do is, we know that with Ohm's law stated up here, that voltage, or potential difference, is equal to current times resistance. So from that, we can think about how the potential difference of the whole series is going to be equal to the current through 1, or sorry, I apologize. We know that the potential difference across the battery is going to be equal to the current, the overall current, because the current through one is equal to the overall current. It's going to be equal to the current times the resistance in 1 plus the current times the resistance in 2. And I did this just by applying Ohm's law. We know that potential difference is equal to current times resistance. So if we want the potential difference across the entire battery, we can do the current times the resistance across the first resistor, and the potential difference called the resistance across the second resistor. Now you might be asking, well, why is resistance different across the different resistors? You said that current is the same over different resistors. Why can't resistance be the same over different resistors? So with Ohm's law here, we have to remember that if current is the same over different resistors in a series, and potential difference is different over different resistors in series, that means the resistance also has to be different, because it always has to equal the current. If resistance was the same over all of the resistors in series, then when the potential difference is divided by resistance, then we would get a different value for the current, but the current is always going to be constant across series. So say we wanted to find the equivalent resistance. If we were to turn this series into a series that just had one resistor, what would that resistance be equal to be equivalent to the resistance in 1 and 2? So back to what we have here, we can do some simple algebra and take out the current. And then we can find the current is equal to the potential difference over R1 plus R2. And so let's bring Ohm's law back down here and look at this. Ohm's law and what I've just written here are exactly the same, except here it's just R and here is just R1 plus R2. So we can conclude that if we wanted to find the equivalent resistance across two resistors in series, it would be equal to R1 plus R2. So let's look at how we would find the equivalent resistance across resistors in parallel. So let's have some resistors in parallel here. Here's our battery. Here is going to be the second resistor. And here is the first resistor. And so we know that current is flowing through like this, from positive to negative. And so let's look back at our river analogy from earlier. But let's change it so that it applies to parallel now. Let's say you have a river here and it's flowing through a tiny little straw like this. It's going through there. Now, what if there was a pathway that it could go up that had way more room, just like this? So, don't you think that more water would choose to take this path across instead of squeezing through this tiny little opening, if all the water's coming from somewhere, which path would you take? Wouldn't you take the wider, more easy path to flow through instead of the tiny little opening here? Well, the same thing happens in circuits. If resistor 1 has much more resistance than resistor 2, then more current is going to flow through resistor 2 because it'll be an easier journey for the positive charges to take. So we know that the current through 1 is not equal to the current that flows through 2. But in fact, we actually know that the total current through the entire across the battery is equal to the current that flows through 1 plus the current that flows through 2. And so we can go back to Ohm's law, and we can apply Ohm's law to what I wrote just right here to find the equivalent resistance across both these resistors. So let's look back here. We know that Ohm's law states that the current is equal to the equivalent, that the current is equal to the potential difference over resistance. What we also know for parallel is that the potential difference is the same across resistors. So we can write out that the total current is equal to the potential difference over resistance 1 plus the potential difference over resistor 2. And then we can, because we know the potential difference is the same, we can take out the potential difference. So 1 over R1 plus 1 over R2. So what does this look like here? If we compare it back to Ohm's law, we can conclude, if we look at Ohm's law here, and we set these equal to one another, let's say this is the equivalent resistance. If this is the current across the entire circuit here, if this is the current across the entire circuit, and this is the voltage across the circuit, then this will be the resistance across the entire circuit. So how would we get, what do we know about the resistance here and the resistance of 1 and 2? We know that 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. And this is how you find the equivalent resistance of a circuit in parallel. So, what did we learn? We learned that the R equivalent of a resistor in series is R1 plus R2. And we know that the equivalent resistance of a resistor in parallel is equal to, or 1 over the equivalent resistance of a resistor in parallel is equal to 1 over R1 plus 1 over R2. And if you want the it to look